All right. Thank you very much. Thank you for the organizers for inviting me for this talk. So my name is Hyun Kum. I'm an assistant professor at Yonsei University, and I'll be giving a talk on flexible oxide films and their heterointegration by remote epitaxy. And most of this work actually was done by me when I was a postdoc at Professor Jiwon's group. So you guys might be already familiar with most of the contents here. And of course, the previous speakers already gave a very nice overview of the first half of my talk, so I'll be flying through my presentation. All right, so, but why is remote epitaxy so important? I think it's because it's a key technology that allows us to achieve what's called ubiquitous electronics. And in other words, electronics that can be deployed anywhere. And to achieve this ubiquitous electronics, we have to achieve 4 engineering goals. First is we have to move away from rigid devices and be able to create flexible devices so that it can be, stuck or deployed on very rough surfaces, non-uniform, non-flat surfaces. And it also allows us to save a lot of money because we are potentially able to reuse the substrate. And that allows us to create very cheap electronic devices that everybody can afford. The second engineering goal is to be able to use any material in the periodic table as opposed to a single material. Today, only one material is very efficient for one type of device, but if we can use any material in the periodic table, then we can create ubiquitous multifunctional devices, and that's the next engineering goal. We want to be able to create a material that has multiple functionalities instead of just single function. It's kind of like the iPhone. If you remember, just 10 years ago, you were carrying your cell phone, your PDA, your MP3 player, but the iPhone kind of integrated all that into one device. So we are trying to create the iPhone of electronic devices through remote epitaxy. And of course, the last engineering goal is to be able to create self-powered devices instead of power-consuming devices, because once these devices get very small and deployed in very exotic places, you don't want to be changing out batteries on those devices. All right, so you guys already know this probably more than better than me. So there are 2 types of techniques to create these integrated films or devices. First is the bottom-up approach, where you epitaxially grow single crystalline material on top of a single crystalline wafer. But this approach has very hard physical constraints that make it very difficult to achieve something like this. For example, integrating single crystalline 3,5, 3-nitride, and oxide materials because of obviously lattice mismatch problems and thermal budget problems. So the better approach is this top-down epitaxial layer approach, where you just grow your single crystalline films, you exfoliate it off of the substrate, and then stack them together like Lego. And there are a lot of methods that's already introduced by previous speakers, such as chemical liftoff, mechanical, optical, and 2D assisted. So to achieve the first and second engineering goal, we have to be able to epitaxially grow your device layer, exfoliate it, transfer that onto another foreign substrate that's more desirable than the host substrate, and then reuse the host substrate. And of course, there are already very established methods to do this. First is the chemical liftoff, but there are, of course, limitations, such it's not scalable, meaning that the bigger the wafer, the slower this process is. Mechanical spalling, it's very quick, but the surface of the exfoliated interface is extremely rough. And the control of the thickness is very difficult. Last is laser liftoff, but this only works for transparent materials such as gallium nitride, high band gap materials. So remote epitaxy kind of has none of that bottleneck, but of course I'll talk about the biggest bottleneck for remote epitaxy later in the talk. And in the interest of time, and since you guys already had a good overview of remote epitaxy, I'll skip through the remote epitaxy portion of this talk. So for my work, I did remote epitaxy of complex oxide films. And if you look at this figure here, we can see that as the band gap of the material increases, we can have thicker and thicker graphene layers. So I was very lucky when I got this project because complex oxides have pretty high band gap, so remote epitaxy works pretty well. For the students that were working on remote epitaxy of gallium arsenide, it was very difficult. So complex oxide is very interesting material because contrary to 3,5 and 3-nitride materials, it can not only be used for logic and memory devices, but also sensors, detectors, communication, energy harvesting storage, actuators, transducers, and also quantum information devices. So actually, you can only use complex oxides to create all these devices and integrate them together in one platform. So the first few iterations of remote epitaxy, I used what's called the pulse laser deposition technique. And this technique was very difficult. I had low yield. So when I first started this remote epitaxy of complex oxide, I only transferred one layer of graphene on the STO substrate. And I found that I couldn't exfoliate it after growth. And after doing a cross-sectional TM, I found out the graphene was actually gone. And that's probably because for pulse laser deposition, you actually ablate a target, which creates a very high intensity plasma, which etches away the graphene. So a quick solution to that was actually to transfer 2 layers of graphene. So the plasma would etch away the first layer of graphene, and the second layer on the bottom would survive. And once you have a very thin nucleation, then the plasma won't damage the graphene underneath. So that was the first iteration. The next iteration, we actually tried molecular beam epitaxy, oxide molecular beam epitaxy. And just as Professor Bharat Jalan demonstrated, MB is a more desirable tool for remote epitaxy of complex oxides because it's a very soft, there's no hard plasma environment to damage the graphene. But of course, using PLD, we were able to see very nice oscillations and layer by layer growth on top of graphene coated STO substrates. And we were able to demonstrate all these different complex oxide materials with different crystallinity, such as STO, which is a perovskite, CFO, which is a spinel, YIG, which is a garnet. And we also did a very detailed TM analysis to make sure that the layer, epitaxial layer that was grown through remote epitaxy had perfect stoichiometry from the interface. And we did yields, very high resolution TEM to verify that there were no defects such as oxygen deficiencies and whatnot. So this shows for an STO thin film. So we exfoliated off of the graphene coated substrate using a Ti adhesion layer and a nickel stressor layer. Right, and this is for a STO film. There are very tiny regions of defects which I'll describe why we have these defects on these films. It's very small island defects. And this is for a CFO film of about 100 nanometers thick. Again, you can see there are tiny islands, defective islands. And also PMMPT, which is a very representative piezoelectric material. And of course, for BTO, ferroelectric material, which you can see from the PFM amplitude of phase measurements. We were also able to demonstrate reuse of the substrate. So this is a graphene coated MAO substrate. And on this substrate, we grew CFO, epitaxial thin films, 3 times and measured its magnetic properties, the hysteresis. And we got, identical hysteresis, all 3 films, and also a perfect single crystallinity of all 3 films. So this is a video that shows you the remote epitaxial process. So this is a tiny sample. It's already epitaxially grown, and I have the tiny nickel handling layer. And first, I would just cleave the sample in half. So the top part, you can see this darker region is a BTO film that's grown on top. And then if you just peel off the substrate here, the blue region, bluish region is the BTO, and then it gets peeled off cleanly from the substrate. So there are some key factors that we identified that lets you successfully do remote epitaxy. First is preferably not use PLD, because PLD is very highly energetic and it likes to damage the graphene. So the better method is to use MB growth. And we also try to use different kind of graphene, such as silicon carbide single crystalline silicon carbide graphene, single crystalline germanium graphene, polycrystalline copper graphene, and single crystalline copper graphene. And also different transfer techniques of these graphene layers, such as dry transfer and wet transfer. So this is the dry transfer method that was developed at MIT. So it's a semi-dry transfer because you still put it in liquid. But you first start off with graphene that's grown on a single crystalline substrate, such as silicon carbide. You deposit a very thin nickel stressor layer, and then you peel it off using thermal release tape. And you just transfer this onto your desired substrate, release the TRT by heating it up, and etch away this nickel stressor layer using FeCl3. And you have your graphene on top of your substrate, and you can stack how many layers of graphene you want. And this is a SEM image of showing you, one monolayer graphene region, two monolayers of graphene region, etc. And you can get very clean transfer as well, because you don't have the PMMA residue when you do the wet transfer. Professor Hyun Kim at Sejong University also did a very nice study showing the differences between dry transfer and wet transfer. He found out that if you do a dry transfer technique, the graphene layer is actually more closely attached to the substrate compared to wet transfer graphene. So if you look at the TEM images here, this is the drag transfer gallium arsenide on gallium arsenide TEM image, and this is for wet transfer graphene, gallium arsenide growth. And you can see that for dry transfer, the surface is very smooth and single crystalline, whereas for the wet transfer technique, you get a polycrystalline film because the distance between the epifilm and the substrate is rather long, right? All right, but transfer graphene is not the best, even if you do dry transfer technique, because obviously if you do it by hand, you're going to have some transfer residues, such as it could be PMMA, it could be some nickel particles that didn't get washed away. And you also have micro tearing of these graphene films. So the best way actually is to directly grow graphene on your substrate, right? So we tried that on STO substrate. You can actually grow graphene on STO. You can see the graphene growth morphology here. It nucleates randomly, and then they get bigger and bigger until they merge, right? But the problem here is that because the nucleation is random, you have regions where it's monolayer, regions where it's bilayer, regions where it's trilayer, right? The thickness is rather random. So to combat this, we used a technique called atomic layer etching. And this is where we can actually etch away layer by layer of graphene, one atomic layer by atomic layer. And you can see that before atomic layer etching, the graphene surface after graphene growth is rather rough, but after 2 cycles of atomic layer etching, the surface is rather smooth, and we get a higher graphene 2D intensity in Raman. Right? So you can see that the results without ALE on directly grown graphene STO substrate, we get a polycrystalline growth because the thickness of the graphene is very non-uniform and rather thick. But with ALE, we can get very nice single crystalline films and very high yield exfoliation. We also found something interesting. So this is not remote epitaxy. This is just atomic separation at the interface. I mistakenly sent out a sample without graphene, and my collaborators grew PMMPT on that substrate. And I deposited Thai nickel and exfoliated. And interestingly enough, the PMMPT film actually exfoliated precisely at the STO SRO PMMPT interface, atomically smooth. If you look at the AFM image of the exfoliated PMMPT, first we thought it was due to these the lattice mismatch with the PMPT and the SRO-STO substrate, but we tried different combination of materials, but for now we couldn't figure out the exact reason why this is happening. And we also saw this when we grew LLTO. This is lithium lanthanum titanate. This is a battery material, right? And we were able to grow single crystalline or highly oriented LLTO and exfoliated precisely at the interface between the silicon carbide substrate. And also we grew LLTO on MAO and we're able to grow single crystalline and exfoliated as well. So I'm going to conclude my talk with the application. So we have to stack them together to create a multifunctional material, right? The stacking method is very simple. It's just your standard wet transfer technique when you transfer 2D materials. And we transfer CFO on top of PMMPT. So PMMPT is a piezoelectric material, and CFO is a magnetostrictive material. So this constitutes a multiferric magnetoelectric device. We applied a voltage across the PMMPT, and in situ TEM saw the lattice change in CFO. So this video here shows you the lattice change in CFO as we apply a voltage across the PMMPT. So if you look closely, you can see that as we sweep the voltage on the PMMPT, the CFO film kind of strains like a beating heart. Right? So we could clearly tell that there was a very strong mechanical coupling between PMMPT and CFO. This is just a still image of the same thing. We also measured the magnetoelectric coupling coefficient of this device. So this is a freestanding device, completely freestanding, and compare that to a device that was bonded to the substrate, we got a much higher magnetoelectric coupling coefficient. And of course, we were able to control the magnetic property of CFO of the freestanding device by applying a voltage across the PMMPT, whereas for the device that was clamped to the substrate, we couldn't change the magneticity of CFO. We also verified that it wasn't just simple mechanical coupling between these layers. We coupled CFO to YIG and found out there is magnetostatic coupling at the interface, and also electrical coupling as well by sandwiching graphene between YIG and CFO. And we tracked the Fermi level of the graphene using Raman techniques by tracking the peak and the full width half maximum, and found out that indeed there are charge transfer between the YIG and CFO membrane to the graphene. And finally, we applied this and used STO, a very thin STO film, as an gate oxide for a GaN-HEMT device. And we found out something very interesting. We were expecting a very big hysteresis response because if you transfer these materials, inevitably you would expect to create defects at the interface at the gate oxide, and that would create charge traps, which would lead to hysteresis on your IV curves. But interestingly enough, we didn't observe any hysteresis. And so we made a device with just your conventional hafnium oxide gate oxide, and there we saw hysteresis. So apparently this transferred STO has a better interface than your deposited hafnium oxide gate oxide. Right, and the subthreshold slope was around 60 millivolts per decade, and this also points towards a very clean interface between STO and GaN. And we tried two different gate metal thickness. So we wanted to actually strain the STO using thicker gate metal. So this is nickel. We use nickel for the gate metal, and for 150 and 450. And we found something interesting. For thin nickel gate metal, we saw some current collapse, but for a strained STO gate oxide, we didn't observe any sort of strain collapse. So apparently the strain is also helping getting rid of interface charges between the gate oxide and the GaN-HEMT area. And finally, we're also working on creating a self-powered devices by developing single crystalline electrolytes that can be used as very thin, flexible, and very tiny batteries. That's extremely safe because single crystalline materials kind of prevent these dendrite formations that can lead to explosion and fire. And those are the acknowledgements. Thank you for your attention. That concludes my talk.
Thank you very much for the nice talk. So because of time limits, so we will only have one question. Is there any question from audience? Okay, there's one question.
Hi, great presentation. Aryan from Penn State. So my question was, it's a very naive question. So the question is, you're comparing hapnia with STO, and you're saying the hysteresis is lower for STO. So has it been very, like in terms of, fabricating more devices? Have you seen that consistently? Have you been able to prove that the interface is always very clean with STO? Because even with hapnia, there have been very good demonstrations with very much reduced hysteresis. So that's
a very good question. We're actually in the process of doing TM analysis on it, but over 6 devices, we found the same trend between hafnium and STO. But of course, the hafnium that we deposited might not be of the best quality. So we're trying to kind of doing analysis to compare those two.
Okay, great. Thank you so much.
Thank you.
More question? Let's go with the one more question here, and then we'll move on to the next speaker.
Thank you, Professor Kum, for your talk. There's one question Zoom Manuel conveyed here. What technique do you use for the stressor layer evaporation? Can you comment on the parameter used and which thickness do you use for the nickel stressor? Is there any sticking layer used underneath? And he does have another question, which is, how do you compare your Raman results? Concentrating on the defect band density, or do you do any normalization for the different Raman results?
So for the first question, we use sputter for the nickel stressor film, and the thickness varies between 500 nanometers to up to 3 microns thickness. So if you really just want to exfoliate your film, you can deposit a very thick, very highly stressed nickel film. But if you wanted to reduce the nickel thickness, maybe you wanted to get rid of the nickel afterwards for transfer and heterointegration, then you would have to find the optimal thickness and the stress. But we use sputter technique because it's easy to control the strain of the nickel film using that method. And as for the second question for Raman, we don't really do a very detailed analysis of the Raman. We just do it to make sure that the thickness of the graphene is how we want it, and also the defect is very low.
Right, thank you. He just added one more short question. Have you been able to stack 2 freestanding membranes? If so, have you been able to characterize them electrically?
So yeah, so I wasn't able to stack 2 electrical membranes, but the CFO PMMPT membrane was that's two heterointegration stacks, and I'm also able to apply voltage across the PMMPT.